CVPR 2025, discussing two papers that are related in the data-driven autonomous driving track. One is building reliable simulation driving agents through self-play, and the other is Scenario Dreamer, which is generating scenarios out of given prompts. So you take images or short videos from actual real driving data, driving scenarios, and you create more general driving scenarios. And both of these papers attempt to create a simulated environment for autonomous driving training. So you want to have an environment where your ego, your agent, your car, in simulation can be trained to drive in traffic scenarios. In order to do that, you have to have some sort of scenario. You have to have a realistic driving scenario. And that's what both of these papers try to attempt. The first paper from Eugene Vinitsky, from NYU is using self-play to achieve that, and Felix Hard from Princeton, the second paper is using diffusion, vectorized latent diffusion. So I'm going to talk about this in more detail. Just before I go there, CVPR 2025 seems like a very interesting conference. I'm actually not physically there, so I'm discussing this remote. I'm looking at the workshops, keynotes, I'm looking at papers. I'm going to try to summarize as much as I can from here. It's not ideal, but it is what it is. The scheduling was such that this year we went to ICRA in Atlanta, and we've foregone the Nashville trip to CVPR 2025. Maybe it was a mistake. It looks like actually there's a lot of robotics work being presented, and we're actually getting more and more interested in the robotic side of things, so the humanoid robot side, the manipulation side, the mechanics, the AI related to robotics. But nevertheless, I think autonomous driving is still, of course, on top of our minds. This is probably the week when the Tesla robotaxi will be launched in Austin, so it's a pivotal week for us Tesla investors. It's a pivotal week for autonomous driving. A lot of the work that is being done here, in my opinion, is foreshadowing what's coming in the real world through Tesla. Tesla has solved a lot of these problems, not all of them, and some of this work is, of course, still ongoing and very interesting. So having said that, let's talk about the papers now. So the first one, building reliable simulated driving agents by scaling in self-play. The paper itself, it's in the show notes. The title is Building Reliable Sim Driving Agents by Scaling Self-Play. A couple of authors, mainly from NYU and a company called Puffer AI. So what these people are trying to attempt here is, the problem they're solving is the following. If we have let's say we want to simulate in virtu traffic scenario, so we have to have a traffic scenario. How do we create that traffic scenario? Well, one way to do it is, of course, to hard code the whole thing. To say, okay, a car's coming, it's turning left, turning right. That's obviously not very productive, not scalable. So what these people are doing is self-play. So through self-play, they're creating traffic scenarios that are useful for reinforcement learning. So what does that mean? So you have a bunch of cars and you train them through reward function shaping. So you don't explicitly tell them what to do, but you give them a reward function. In this case, what they're telling them is don't collide and stay on the road. And the rest, let's just let it go. Like, there's not a lot more constraints. I mean, there's a little bit more, the technicalities are in the paper. You could write a whole paper and have a whole conference about what kind of reward shaping you actually want for a self-play scenario in simulation, right? You could think about that, but I think that's not the main purpose of this paper. This paper is assuming a certain reward function design, and through self-play creating scenarios that are realistic and robust. That's important. What does robust mean? Robust means that that in certain scenarios, that that happens every time the scenario comes up, right? It's not like random, one time he turns left, one time he turns right at the same stop sign, that kind of thing. It's relatively robust over time. The reinforcement agent actually creates nominal agents, which are the agents that your actual virtual agent is exposed to. The nominal agents start behaving in a certain coherent way, which is exactly what you want from a simulated traffic scenario. I think the bigger context of this paper, of course, is the ability to train a car in self-play like AlphaGo Zero. That's the North Star. I think that's where we are heading as a community in embodied intelligence, that we're going to in-virtu train agents and then have the sim-to-real transfer, and then actually have them apply what they've learned in the reality. We're still not, we're probably maybe 2 years away, I would say. Nevertheless, I think this is the right path, and I think that's one of the interesting things about CVPR, that we actually have quite a few papers about this. So this means it's happening. Now, the actual workflow is you're starting with a data set, the Waymo data set for traffic scenarios. You use them as prompts, and then you generate draft scenarios through self-play. You then fine-tune the whole thing with out-of-distribution scenarios. One key observation in reinforcement learning is that there's no such thing as bad data. So when you have a reinforcement learning agent that learns in self-play, you can actually think of reinforcement learning as a synthetic data generation engine. And all the data are useful, even the bad data. So we take a certain, let's say we take a Waymo data set with a traffic scenario at a stoplight in Los Altos. There's cars coming from the left, cars coming from the right. And now in self-play, you're copying many iterations of that scene. So the car that's coming from the left stops, doesn't drive, even though it has green, the car drives, but the car from the left goes too far, maybe almost collides, then the others have to stop. So there's a lot of different scenarios. A lot of them are bad scenarios, but your reward function design is such that you want to avoid collisions, stay on the road. So with all the bad data, bad in a sense, the data that is, that is not what you would want to see in actual traffic scenarios. But nevertheless, having a lot of these weird scenarios will allow you to train the agent and to avoid these types of scenarios, because it's not getting rewarded for, to avoid scenarios. So if it happens, if such thing happens, if other distribution scenarios happen, it knows how to avoid them, because it's not being rewarded for something that is not favorable in a scenario like that. So my point here is that reinforcement learning as a synthetic data generation engine, I think, is a concept that is a little bit underappreciated, because we always talk about data scarcity in robotics, and I think this is the way to overcome data scarcity. The next paper I want to discuss is Felix Hardy from Princeton et al. Self-play scenario dreamer, vectorized latent diffusion for generating driving simulation environments. So this paper, really the main contribution is vectorized latent diffusion. So you take a traffic scenario and you translate it into vector space, and then you use diffusion on the vector space. So you're kind of overcoming some of the inefficiencies with pixel-based computer vision, right? If you take pixels, you take the canonical example is you have a scenario where a car drives on the street with trees, and you don't need to represent all the pixels of the tree and the background of the tree. What you really need is fundamentally only the actual, the stump of the tree. You need the environment around the tree. You need certain things are important for collision avoidance, and then of course if you have pedestrians, you have behavioral modeling, which is also added in the paper. But fundamentally, again, the main contribution here is really the fact that you're using a given image or let's say a short video. you're translating into latent space, and then using diffusion to generate scenarios, again, for in-sim reinforcement learning. What's interesting, just a few mentions in the paper, is one is that they've noticed that they've pushed the planning agents that are available quite to the extreme with their scenario generation. So they've been able to generate scenarios that show the limits of the kinds of planning that are at least off-the-shelf type planning algorithms that are available. Now, I don't know exactly which planning algorithms they're talking about, and we as Tesla investors, of course, always come from the Tesla perspective, and we say, well, look, we already have FSD, which is driving in very complex real-world driving scenarios. So for us, all this theoretical work seems almost redundant. But I don't want to go that far, because I think all of these endeavors are at worst only incremental, and sometimes they could actually have some interesting insights. We shouldn't underestimate. I think the scenario analysis, the scenario generation, and the self-play on its own have a lot of merit for robotics going forward. The fact that Tesla has solved a lot of the self-driving problems, at least the rudimentary self-driving problem, which is the navigation on the roads without collision, staying on the road, obstacle avoidance, all of these things have been solved. But what's lacking there, of course, is the semantics. So we're still having trouble with understanding, for example, a person that is waving either to stop or to come, like things like that are still, I don't know if the latest version of FSD can do that. I am on hardware 3 with a 12.6 version, and there it's a little bit tricky. Sometimes it works, sometimes it doesn't. So I guess to summarize these two papers again, I think important data-driven autonomous driving and self-play. This track is all about, of course, interesting new methods in using data-driven methods to train autonomous vehicles. So, and one of them, of course, is reinforcement learning in simulation, which I think is the future. Self-play a la AlphaGo Zero. The paper number 1 out of NYU is solving the scenario generation problem through self-play. The second paper is solving it through vectorized latent diffusion. Thank you.